Welcome back to our regularly scheduled program, Things That Go Beep Underground. Today's feature, CSL, Cross-Hole Sonic Logging, in glorious technical detail. Picture this. We're sending ultrasonic pulses through your concrete like a dolphin trying to find fish. Except the fish is structural integrity, and the ocean is 80 feet of hardened cement. The results appear on what we call a waterfall diagram, which sounds way more relaxing than it actually is. Here's what we're looking for. FAT, that's first arrival time, not your uncle at Thanksgiving. If FAT is constant, good, you're winning. If you see an anomaly, late arrival or low energy, that means something's blocking the signal. Either you've got a defect or the concrete is being lazy. The physics? Simple. Velocity equals distance divided by time. We're targeting around 13,000 feet per second, which is roughly how fast gossip spreads in a small office. Anything slower, and Houston, we have a problem. Specifically, a concrete problem, which is worse than most problems because you can't just turn it off and back on again. Next up in our testing trilogy, LST, low strain testing, also known as pulse echo, also known as professional shaft thumping. Here's how it works. You impact the top of the shaft, basically giving it a controlled bonk, and listen to the echo. It's exactly like yelling into a canyon, except the canyon is concrete, and you're using fancy sensors instead of your voice. An early reflection? That indicates a potential bulge or neck. Your shaft is having shape issues. A toe reflection confirms the length. We're making sure the shaft reaches all the way down like it's supposed to, not just giving up halfway because it got tired. But here's the catch, and there's always a catch. Below 30 diameters depth, this method gets difficult to interpret. It's like trying to hear someone whisper from across a football field during a rock concert. Theoretically possible, practically frustrating. For really deep shafts, this method waves the white flag and says, "You're on your own, buddy." That's when you call in the big guns. CSL. Time to get hot and heavy with TIP, Thermal Integrity Profiling. This is the method that proves concrete has feelings. Well, temperature, but close enough. When concrete cures, it generates heat through hydration energy. It's basically having a chemical party down there, and we're measuring the party's temperature. The result? A beautiful heat map that looks like something from a weather forecast, except instead of rain, we're tracking concrete quality. High hydration energy? That's sound concrete, the good stuff, partying appropriately. Cold spot? Uh-oh, that's necking or inclusions. The party died. Someone brought dirt to a concrete party, and now everything's awkward. The advantages? You can test early, just 12 to 48 hours after the pour. No waiting around for weeks like CSL. Plus, it finds external soil inclusions that snuck in uninvited. And here's a bonus. If the heat is off-center, your cage has shifted. It's like discovering your picture frame is crooked, except the picture weighs 50 tons and is underground. Tip: helping you see heat since, well, whenever they invented this. I should have looked that up. Time for the ultimate showdown. CSL versus TIP. It's like Batman versus Superman, except with way more spreadsheets and zero capes. Let's set the stage. You've got a project with 7 shafts. Sounds simple, right? Wrong. Welcome to logistics hell. CSL consumables. Steel pipes. Heavy, costly, and about as fun to transport as an angry rhinoceros. TIP consumables, thermal wire, light, cheap, and way easier to explain to accounting. CSL site visits, 7 trips. 7. You've got to wait for curing, come back, test, repeat. It's like having to go to the DMV 7 different times. Your schedule is weeping. TIP site visits, 1 trip. You install it, it auto-logs, you're done. You're home in time for dinner. Your family remembers what you look like. The verdict? TIP has higher upfront material costs, but the engineering and schedule savings are massive. It's like buying the expensive coffee maker that saves you from Starbucks trips. Math wins, everyone's happy, and you've got more time for important things, like creating humorous slide narratives about foundation testing. Ladies and gentlemen, introducing the engineering equivalent of a magic trick, the O-cell. It's bidirectional load testing, which means the shaft literally tests itself. Mind equals blown. Here's the genius. We embed a hydraulic cell inside the shaft during construction. Then we activate it, and it pushes both ways, up and down simultaneously. We measure side shear resistance going up and end-bearing resistance going down. It's like the shaft is doing a structural push-up, and we're counting the reps. The beauty? No surface reaction frame needed. Traditional load tests require massive steel frames at ground level to push against. Those frames are expensive, heavy, and generally a pain in the assets. The O-cell eliminates all that. The shaft is its own gym, its own personal trainer, its own motivation. It's bidirectional testing at its finest, proving that sometimes the best way to test something is to make it fight itself. Deep. Also effective. Buckle up, because we're about to talk about Statnamic, aka the rocket launch method. And yes, it's exactly as awesome as it sounds. Picture this. A reaction mass sitting on top of your shaft. We ignite a combustion chamber. Boom! The reaction mass launches upward with 20 grams thrust. And by Newton's third law, an equal force slams downward into your shaft. We're talking 5,000 tons of force delivered in m. It's fast. It's basically the action movie of foundation testing. Michael Bay would be proud. Somewhere, an explosion just happened in slow motion while this test was running. Traditional static load tests take hours or even days to gradually apply load. Statnamic? Milliseconds. You blink and it's done. The shaft doesn't even have time to complain. Perfect for busy schedules, tight budgets, and engineers who like things that go boom in a controlled, professional manner. Side effects may include extreme excitement, the urge to high-five everyone on site, and an inexplicable craving to test more shafts. Consult your structural engineer before operating heavy combustion equipment. Welcome to the classification system, where we turn messy NDT results into crystal clear decisions. It's like Marie Kondo for foundation testing. Does this reflection spark joy? If not, investigate. Let's break down the classes, shall we? Class AA, sound. Clear toe reflection plus normal velocity equals accept. This is the gold star, the A+ grade, the chef's kiss of foundation testing. Your shaft is perfect. Frame it. Celebrate. pop champagne made from concrete dust. Okay, don't do that last one. Class AB, no major defect. No toe reflection, but also no early reflection, equals accept. It's like getting a B+. Not perfect, but good enough for government work, which, ironically, this often is. Class PDX, probable defect. Strong early reflection, equals investigate. The X stands for X marks the spot where we need to dig deeper, metaphorically speaking. Time to call in backup testing. Class IR, inconclusive. Poor top quality or too much noise, equals retest. It's the equivalent of, "Sorry, I couldn't hear you over this jackhammer. Can you repeat that?" But for concrete. This systematic approach ensures structural integrity through expert interpretation. Translation? Hire people who actually know what these squiggly lines mean, because guessing is not an acceptable strategy when buildings are involved. Time to talk about concrete strength verification, arranged conveniently on our patented cost and reliability scale. From cheap and cheerful to expensive but honest, let's rank our options. Standard cylinders, low cost, reliability. The baseline. We take concrete samples during the pour, make cylinders, cure them, test them. It's like keeping a food sample to make sure the batch was good. Problem? Those cylinders had a spa day in perfect conditions. Your actual shaft was underground fighting groundwater and questionable soil like a UFC fighter. Not quite the same experience. Rebound hammer, medium. Also called a Schmidt hammer. Sounds fancy. You literally bounce it off the surface and measure the rebound. It's surface-only testing, which means you're judging a book by its cover. Sure, the cover looks great, but what if the middle chapters are garbage? Useful for quick checks, terrible for deep investigation. Coring. High cost, reliability. The absolute truth. We drill out a core sample from the actual shaft, the real concrete that's been through the real conditions. Then we test it in a lab. It's expensive, it's invasive, it's time-consuming, and it's the final arbiter for PDX classifications. When you need to know beyond any doubt, you core. It's the lie detector test of concrete verification. No arguments, just facts. Uh-oh, we found a defect. Don't panic. Welcome to anomaly mitigation, or as I like to call it, fixing your underground oopsies. We've got 3 strategies in our repair toolkit. Option 1, grouting. See that void? That gravel zone that shouldn't be there? Let's just fill it with grout. Permeation grouting uses tubes to inject material and fill the gaps. It's like using spackle to fix a wall, except the wall is concrete, underground, and holding up a bridge. No pressure. Option 2, replacement. When grouting won't cut it, when there's actual structural failure, we bring in the big guns, micro piles or new shafts. Basically, we're admitting defeat on that shaft and building backup support. It's the Control-Z of foundation work, except you can't actually undo the bad shaft, you just work around it. Expensive? Yes. Necessary? Also yes. Option 3, engineering analysis. Before we panic and spend a fortune, let's ask the critical question. Is the defect in a critical stress zone? Maybe it's in a low-stress area where it doesn't actually matter. Engineers do calculations, run models, consult their coffee mugs, and determine if the defect is a real problem or just cosmetic. Sometimes the answer is, it's fine. Those are good days. Choose wisely. Your budget depends on it. And now, for the grand finale. Let's wrap this up with the summary checklist. Your cheat sheet for drilled shaft glory. Preparation. Know the ground. Perform a technique shaft. Don't go in blind. That's like cooking a new recipe without reading it first. Possible, but you'll probably set something on fire. Excavation. Maintain fluid head greater than groundwater. This is not a suggestion, people. Groundwater is not your friend here. It will ruin your day and your shaft. Keep that fluid level up like your life depends on it, because someone's life might actually depend on this foundation. The pour. Keep the tremie buried. Track the volume plot. If I've said it once, I've said it 1,000 times. Buried tremie equals happy shaft. Watch that volume plot like it's the season finale of your favorite show. Deviations equals plot twists you don't want. Verification. Clean the bottom. Test integrity with CSL or TIP. No sediment, no shortcuts, no excuses. Then verify with proper testing, because trust but verify isn't just a political slogan. It's literally how we make sure buildings don't fall down. Final wisdom. Quality assurance is insurance. You can cheap out on a lot of things in life. Foundation integrity is not one of them. Do it right, document everything, test thoroughly, and sleep soundly, knowing your shaft can handle whatever the world throws at it. That's a wrap. You've now completed Drilled Shafts, the complete saga. Your certification is in the mail. Just kidding. You need actual credentials for that. But you're definitely smarter than you were 20 slides ago, and that's worth celebrating. Now go forth and build responsibly.